Okay, so we're talking about absolute convergence, and we've got some problems here we're going to apply. So I'm looking, and I've got my sequence an is equal to negative 1/2 raised to the n power. Now I want to consider the absolute value of the sequence. So the absolute value of negative 1 to the n over 2 to the n, I just simplified with algebra here. This is going to be equal to, well, what's the absolute value of a negative? This becomes a positive, okay? 1 to the n over 2 to the n. So this is 1/2 to the n power here. That's all that's going on here. No big deal. All right, so we consider the series n equal 1 to infinity, absolute value negative 1/2 to the n, okay, which is equal to a series n equal 1 to infinity of 1/2 to the n. Why do we do this? Look, when you run through your test, always check for absolute convergence first. If absolute convergence is a success and it converges, then we know that it also converges conditionally, right? That's just given, it's convergent. But if absolute convergence fails, then we test for conditional convergence. So if you test for conditional first and you get success, then you're going to have to test for absolute convergence. So you're going to have to do it anyway. So you go ahead, you try to get 2 birds with 1 stone, if it's possible. And if not, then you go to test conditional. And if it's not conditionally convergent, then it's divergent. Okay, so check the stronger, the harder thing to do first. And if the harder thing is true, then for sure the lesser is true. Okay? Some logic going on there. Look, guys, this thing right here, this is a geometric. I see a ratio to a power n here. I should think geometric. It's a geometric series with a, the first term. I plug a 1 in, I get 1/2. Okay, a equal to 1/2 with a common ratio r equal to 1/2. Okay, I multiply by 1/2 each time to get the next term. So what does that tell me? Absolute value of r is equal to absolute value of 1/2, which is 1/2. That's less than 1. And this tells me that I'm convergent. Okay, by our geometric series test. So since the series n going from 1 to infinity, the absolute value of negative 1/2 to the n converges. Okay, what did we want to know about? We wanted to know about this series here, not the absolute value, right? Then the series n equal 1 to infinity of negative 1/2 to the n also converges. Okay, this also converges. All right. Next up, series n equal 1 to infinity, negative 1 to the n over n. We've already worked this problem a couple of times, but I want to show you how to work this problem using our new toolkit. Okay. It's always fun to get more tools, right? So how do we do this? Well, an here is negative 1 to the n over n. I want to know the absolute value of an. This is the absolute value of negative 1 to the n over n, which equals 1 over n. Okay, so that absolute value gets rid of the sign switcher. So now what we're going to do is we're going to consider the series n equal 1 to infinity, the absolute value negative 1 to the n over n. What does this equal? It equals the series n from 1 to infinity of 1 over n. Okay, this is divergent. Why? It's a p-series with p equal to 1. P-series, p equal to 1, which is less than or equal to 1. So what does that tell me? That tells me that A sub n, absolute value, the series diverges. Now, what are we going to do since that failed? Now, we check for conditional convergence. Okay, we check for conditional convergence. How do we check for conditional convergence? I do this by the alternating series test. N equal 1 to infinity, negative 1 to the n, an. Alternating series test. If I run the alternating series test, what does this mean? So this is, or my an here is 1 over n, which is greater than 0 for n greater than or equal to 1, okay? The limit as n goes to infinity of 1 over n is equal to 0. And what else do I know? A sub n is greater than or equal to a sub n plus 1. Is this true? 1 over n greater than or equal to 1 over n plus 1? Well, I know all those terms are greater than 0, right? So that tells me that the reciprocals, n plus 1, is greater than or equal to n. And that is definitely a true statement there. Okay, so this is true. Okay. Therefore, the series n equal 1 to infinity of negative 1 to the n with the sign changer, okay, converges by alternating series test. Thus, the series n equal 1 to infinity, negative 1 to the n over n converges conditionally. Converges conditionally. Why does it converge conditionally? Since the series n equal 1 to infinity, absolute value, negative 1 to the n over n, diverges, and the series n equal 1 to infinity, negative 1 to the n over n converges. Okay? So this is what we're looking for right here. All right. So that kind of summarizes everything you got going on there. So now you can see it all in its entirety right there. We're going to do one more example. Okay. So I want to determine if the series sum, oh, that's an ugly sum, sum n equals 0 to infinity, negative 1 to the n, e to the negative n squared, absolutely or conditionally converges or diverges. Okay. So it's either going to be absolute convergence, conditional convergence, or divergence. That's what we're looking for. Okay. Now, what does your gut say? Well, let's just start off with our an. So an here, negative 1 to the n, e to the negative n squared. Let's consider the absolute value. Okay, absolute value, that's going to drop out the negative 1 to the n factor. Okay, and so what does this equal? This is 1 over e to the n squared. Now 1 over e to the n squared, this is an exponential on steroids, right? So it's not 1 over e to the n, but 1 over to e to the n squared. All right, so I'm going to guess converge. I think I'm okay with that guess. So what do I want to do to show that this thing converges? Well, I probably, what this is, because of this n squared here, it's kind of messing up the geometric. So I can't compare with a geometric. I mean, maybe I could. I don't know. Maybe you could. But what I would do is, if I'm thinking that it converges, I want to pick something. Okay, so I'm thinking that the plane is gonna land, right? So I want to pick a series that's bigger than my plane that I know lands, and then what does that tell me? The series underneath has to land. Does that make sense? So I'm going to be using, I guess, the direct comparison test here. Okay, so this one, maybe have to brush the dust off, right? So let's think about this. Something that we know converges that's bigger than 1 over e to the n squared. Well, maybe consider series n equal 1 to infinity 1 over n squared. Okay? Now, what do we know about this? We know this converges by p series, okay, with p equal to 2, which is greater than 1. All right, so we know that that converges. Now all we need to show, so we want to show that 1 over n squared is greater than or equal to 1 over e to the n squared, okay, for n greater than or equal to 1. So is this even possible to show? Well, let's think about this. If I flip it around, my inequalities flip around, what do I get? I get n squared less than e to the n squared. Yeah, I think that's safe to say, don't you? N squared is not as big as e to the n squared for n greater than or equal to 1. So once we get past 1, e to the n squared is beating the dog fire out of n squared. Okay, so this is true. All right, that's a true statement. So I've got a series. Now let's think about the conditions for the direct comparison test. Okay, the direct comparison test says that I need to have what? If the series n equal 1 to infinity of Bn converges and An is less than or equal to Bn for n greater than or equal to 1 here, okay, then the series n equal 1 to infinity of An also converges. I know that Bn converges by the p series, okay? And then I just showed that my Bn is greater than my An for all n greater than or equal to 1. So therefore, so you don't have to write this down. This is just a direct comparison test for a reminder for you. So by the direct comparison test, okay, the series n equal 1 or 0 rather to infinity, okay, of e to the negative n squared converges since what? Since 0 less than, 1 over e to the n squared less than or equal to 1 over n squared, and the series n equal, let's say 1 to infinity of 1 over n squared converges. I know you might be thinking, wait a second, Mr. Clark, this starts at 0 and this starts at 1. Now, I can't start this one at 1 or at 0 because if I start at 0, I'm dividing. So that's just one term that gets dropped out. So technically, you could say that this would start at a 1. And then if this thing converges in from 1 to infinity, then I can add one term to that, add the term n equal to 0. If I add a finite number of terms, then the series still converges. So that's kind of a nuance there. If you're, if that's kind of bugging you, you're like, why is it, why are the indices different here? So, that's some hand waving going on there for you. Then, what can I say? Then the series n equals 0 to infinity of what we really wanted to show, negative 1 to the n, e to the negative n squared, converges. But it just doesn't converge conditionally, it converges absolutely, since the absolute value of the series converge, or the individual terms' absolute value converges. Okay? So very, very powerful there. Okay? So kind of give you a bird's eye view of that whole problem. All right, guys, that sums up